Hey loyal fans, in this fast-breaking story, the internet is dying. Well, not dying exactly, but morphing from a human conversation into a dark bazaar where your private information is sold to the highest bidder. This is true, and it depends on one thing, your continued enthusiastic participation. If you stopped relying on the internet, it would expire, or even better, it might regress back into an open forum for ideas and sharing. Want my advice? Disentangle yourself. Treat the internet as a utility, not a necessity. Find new activities that are closer to nature. Start projects where you play an active part. Choose activities that teach you more about the natural world. This video teaches you about one such activity. When I was 12, there was no internet. There were no computers. There were no transistors or integrated circuits. My isolation was nearly perfect. I was first made aware of a wider world by radio. In those times, radio was so astonishing that we described it by what it didn't require. We called it wireless. Obviously, radio still exists. Some might argue that radio relies on the internet, but it's the other way around. Radio is an independent domain, and by learning about it, you might acquire a sense of the wider world. You might develop skills that can't be imitated by robots and AI. This background image is a modern radio receiver picking up various electronic gadgets in my neighborhood: remote controls, home automation devices, environmental sensors, car keys, air tags, pagers, cell phones, all floating around in space. And this is just one radio frequency. In this video, I'll show you how to set up this receiver and how to use radio to explore a world outside the internet. So let's get started. SDR stands for Software Defined Radio. It differs from traditional radios whose abilities were literally hardwired into the electronics. By contrast, an SDR can change what it does on command. Here's the basic layout of an SDR system, including an external signal detector/converter and a computer program that processes and displays what's detected. Before moving on, I want to point out that, as amazing as an SDR is, it's just become much less expensive. Here's the old setup from a few years ago. Notice that two external converters were required, one to convert signals from 25 MHz to 1.7 GHz, and one to provide an important frequency range not accessible with the original device. The problem was, these modules were pretty expensive, almost $100 in combination. In the new setup, a single less expensive module combines the abilities of the original two, and at a lower price. I want to say, I have no connection with any of these vendors, and I'm only reporting, not profiting. On that topic, for newcomers to my channel, I have no economic stake in my videos. All I care about is educating people. Notice the internet address at the bottom of this slide. It's a resource page on my website for this video that explains how to set up this SDR. The address is also in the description, so you don't have to transcribe it from the display. I should add that the SDR program that runs on your computer and processes the information received by the external module, this program, is free and open source, so the only cost is the external device. This is all explained in the linked page. Here's a little radio theory. Scientists found that if you make electricity in a wire change direction fast enough, some of the energy will escape from the wire and travel through space. Then, in a nice symmetry, they discovered that if you put up a second wire, it will collect some of the energy created by the first wire. The first radio transmitters were little more than artificial lightning generators, batteries, spark gaps, sort of a classic Frankenstein laboratory electricity display. The first applications of radio used spark gap transmitters prior to the invention of the vacuum tube, the latter of which allowed generation and reception of pure single frequencies. People first used radio transmitters to send Morse code, thus creating a telegraph without wires. Morse code communication was reliable but slow. The first voice transmitters used what is called amplitude modulation, in which the information to be transmitted causes the radio wave to change amplitude. These radio signals were very easy to detect. One could use a simple device called a crystal radio. Here's a graph of an AM, or amplitude modulated, radio wave. Here's a graph that shows how the red modulation, that's the information, maybe music or an announcer's voice, changes the amplitude of the so-called carrier wave. The carrier wave has that name because it carries the modulation out across space. Newer transmitters might use FM, or frequency modulation, which has advantages when high sound quality is desired or noise might interfere. Notice that the waves in this graph are alternately compressed and stretched. That's how an FM wave appears when analyzed. There's a more exotic kind of transmitter that, in the name of efficiency, does away with everything but the information we want to transmit. To explain this mode, I need to switch from a time-based graph to one based on frequency. Notice about this graph that the horizontal axis is not time, but frequency. To explain how this special transmitter works, let's start with the frequency spectrum of a classic AM transmitter. The carrier wave appears at the center, a vertical spike, and the modulation appears to the left and right in what are called sidebands. It turns out that an AM transmitter wastes 75% of its energy on a carrier signal and a duplicate sideband. Some time ago, radio engineers realized they could transmit, wait for it, just one sideband, and let the receiver turn that single sideband into a readable signal. In this live demonstration, I show how a modern receiver decodes a single sideband, or SSB, signal. Notice that the music sounds distorted right now. So what's wrong? Remember that this special transmitter mode does away with the carrier wave, but that carrier wave is essential to decoding the information in the sideband. So a modern receiver uses a locally generated carrier signal as a substitute. There's an important limitation, however. The local carrier wave must have exactly the right frequency, or it will distort the signal. Notice that the sidebands are separately processed in the receiver. Lower and upper sidebands are managed independently. This means, apart from being more efficient, two SSB transmitters can occupy the same spectrum that one AM transmitter would have required. Now that I've explained single sideband, which needs a deep description, let me show a more organized survey of the common reception modes available with a converter module and a program like SDR++. I've sorted the modes by required bandwidth, starting with continuous waves, or CW, meant for Morse code, single sideband, or SSB, for voice, old-style AM, amplitude modulation, for broadcasting, narrowband FM, frequency modulation, used by businesses, military, and police, and wideband FM, such as is used in commercial broadcasting. This survey leaves out HDTV, high-definition television, but that's not accessible in this SDR setup. Let's start with CW, or Morse code. For these demonstrations, I'm using my own signal generator, created using GnuRadio. I'll describe that later. My generator's dialog appears at the right. In these tests, I'm generating and receiving signals using a closed-loop circuit, as shown here. Now I'm changing modes to true CW. Wait a minute, let me just get things going here. And this is wideband single sideband at the moment. But I'm going to switch over to CW to show the difference. This is extremely narrow band. CW only requires 1 or 200 hertz of bandwidth to accomplish what it needs to do. CW transmissions, because of this narrow band, can be effected with less power over a longer distance than any other radio mode. Ham operators have contests to see how far they can transmit using what they call QRP, Quebec Romeo Papa, which means maximizing range with the smallest amount of power. I have a few more single sideband comments. I always use music to test an SSB receiver's abilities, because if anything goes wrong, you can tell right away. I'm starting in AM mode just to show the transition to single sideband. When I switch to single sideband, the carrier disappears, and the central spike disappears, and the audio becomes distorted. This is a reminder that the receiver has to provide a carrier. I've mentioned that single sideband tuning is an acquired skill. And sometimes the issue is determining which sideband is in use. A modern receiver should prevent one sideband from being audible on the opposite side. That's certainly true here. AM radio is the easiest to describe, the easiest to receive, and by far the most wasteful of power. You can detune the receiver without noticing or caring. But there's one aspect of AM broadcasting that escapes most people's attention. In distant or DX reception, the expected carrier wave sometimes gets nulled out because of something called multipath. And this makes the AM signal sound like receiving a single sideband signal, but without benefit of a locally generated carrier. Under those circumstances, you're better off using your receiver's single sideband capability. Doesn't actually matter which sideband you use. Narrowband FM has a number of advantages over AM, and it's easier to deploy and use than single sideband. One advantage of FM is that above a certain signal level, it's essentially noise-free because the receiver only cares about frequency changes and ignores amplitude variations. Notice the difference between the FM and AM at the same signal strength. Another advantage, somewhat more technical, is that an FM receiver can use something called a phase-lock loop detector, which can reliably lock onto a signal well below the prevailing noise level and make it perfectly readable. FM requires more bandwidth than single sideband, but at common FM frequencies, reliably detecting and using a weak signal is a more important issue than bandwidth. Narrowband FM is the default choice for untrained radio users. This is wideband FM. I've muted the receiver for this section, not wanting to risk rebroadcasting copyrighted material. Wideband FM is used primarily to broadcast high-quality audio, plus in its modern form, a number of services that are digitized and ride alongside the main FM channel. This extra digital content named the RDS, or Radio Data System, appears in this spectrum as rectangular sidebands, here and here. They contain a digital version of the main broadcast, plus other information useful to radio listeners. Some RDS data appears here at the upper left, in this case the name of the composition being played. Wideband FM requires the widest bandwidth of any I've covered, 200 kilohertz. That's the equivalent of 1,000 code channels, or 67 single sideband conversations. In this section, I show some SDR reception examples. Remember that the RTL SDR v4 device I'm using covers a very wide frequency span, from 500 kilohertz to 1.7 gigahertz. Also, I have some pretty good antennas, a disc cone for very and ultra-high frequencies, and a 100-foot long wire for the HF bands. Let's start with a classic time synchronization station. It's called WWV and has transmitters in Colorado and Hawaii. Transmits on frequencies of 2.5, 5, 10, 15, and 20 megahertz. Now that computers have network-based ways to synchronize their clocks, I use WWV to make sure the network method is working. Well, apparently so. Here's a single sideband ham radio conversation on the 40-meter band. With a modern stable receiver for clarity and comprehension, single sideband reception is often superior to AM. Here's a narrowband FM conversation on the 2-meter band, relayed through something called a repeater, which is a sort of relaying transmitter. For high frequencies like this, transmission and reception must be line of sight, so repeaters located on hilltops greatly increase a station's range. Here's a shortwave broadcast in Chinese. At least I think it's Chinese. The announcer has a peculiar accent. I looked up this station and discovered it's a religious station in Texas. I guess that explains the accent. It turns out one can look up a shortwave station by frequency and time at this website. I know my goal in this project is to wean people from the internet, but this is quite a useful resource. Remember the name Shortwave Info. Here's an example in which the SDR++ program's controls can be used to eliminate a so-called heterodyne, an interfering tone. The heterodyne is located to the left of the carrier frequency, so instead of decoding using the AM mode, we can select one sideband, whichever sideband removes the interference. I began with the lower sideband to make a point. One must choose the correct sideband for this idea to work. Here's an ultra-high frequency example seen earlier, and one that receives home automation and other signals from an entire neighborhood. I found that using wideband FM, even wider than for broadcast, catches more signals. I decided to locate my car key's frequency, and here it is. The signals are synchronized with my button presses. Contrary to what you may have heard, there are legitimate reasons to find such a frequency. An obvious one is to find out whether your car key is actually emitting a signal. I wired my house with the so-called Z-Wave system for home automation. This frequency is one that Z-Wave uses. I tuned this frequency to test my controls and troubleshoot network issues. Same idea as testing a car key. This is the so-called Family Radio Service, or FRS, a band of frequencies set aside for unlicensed radio users. It's like Citizens Band radio, but much better. Higher quality transceivers, better voice quality. Because of the frequency is pretty much line of sight, which for many people is an advantage. More privacy, more chance to find an open frequency. I recently discovered people are allowed to set up repeaters on the FRS band. This is an example. You can tell it's a repeater because the original signal goes off, then the repeater itself shuts down a few seconds later. I decided to mute any identifying content in this example.
Okay, heading 250 Alaska, 537.
Here's some exchanges between aircraft and ground in my neighborhood, including some airliners approaching and departing a regional airport.
Delta 340, roger.
And Seattle, hello, Delta 728, 186, descending 12,000, and 250 knots by Jackson. We have information Foxtrot. Roger on the rhyme, and 165, Delta 728, thanks.
This has been a brief overview and sample of radio signals easily acquired using an SDR. Let me add that SDR activities are unfiltered, spontaneous, and require your involvement and participation. In other words, radio is everything that the modern Internet isn't. In this section, I describe my test signal generator, which I use to create the tutorial displays in this video. One of my goals in this project has been to create both a reliable software-defined radio and a source for test signals available on multiple platforms. Here's the signal generator setup I've been using. It requires a radio signal source. I happen to have a HackRF1 acquired for other projects. Less expensive radio signal generators may exist. I haven't researched this issue in depth. Here's the GnuRadio block diagram. It's available at the displayed link. Needless to say, free and open source. This is my effort to create a generator that provides all required modes in a single package, user selectable through its interface. Here are the relevant mathematical equations for the generator. After reviewing the math, which provides the ideas behind the modulation schemes, creating code is easy. And contrary to what you may read online, the single sideband method is self-evident once you understand the role played by complex numbers. Here's one of my favorite Richard Feynman quotes. "Hey, don't take this the wrong way. I'm not posturing as a math genius. I love math, but I don't understand most of it, apart from a few areas like electronics and orbital mechanics. But that's not surprising. I love women, and I don't understand them either." On Linux, installing and running SDR++, HackRF, and related programs and drivers is easy. But then Linux isn't constantly trying to sell you something or steal your private information, which Microsoft is certainly doing. As time passes, Microsoft is building more and more advertising into Windows and thinking of ways to keep users from disabling the ads, not unlike the Internet itself. In fact, the only reason I wrote this generator using GnuRadio Companion is because I couldn't get my Python and Rust versions of the generator to run properly on Windows. The underlying problem is that Microsoft doesn't own Python, doesn't own Rust. Therefore, they don't deserve support. During this project, my worst Windows moment, no shortage of those, was when Windows rejected an effort to create an anonymous pipe between a modulation source and a signal generator, which on Linux is child's play. Windows rejected the pipe, crashed the process, then refused to kill the zombie process the failure created. To run another test, it was necessary to, wait for it, reboot Windows. No, boys and girls, I'm not making this up. Anyway, GnuRadio is an education and creation environment, so installing it is worthwhile apart from this project. You can learn a lot from it. I want to show you my first radio. Well, almost my first. I built a crystal set before this. In the summer of 1956, age 11, I picked apricots for 2 months to save enough money to buy a Heathkit AR3, a tube-based general coverage receiver that was popular at the time. In kit form, the radio cost $27.95. I won't bore you with the financial details, but in 1956 dollars, that's a lot of apricots. On the topic of being poor when young, just don't get me started. We were so poor, we had to rent inferiority complexes. We were openly envious of our neighbors who owned their inferiority complexes outright. Consider the context of the times. Transistors had been invented just 9 years before and weren't yet available for consumer products. And within 10 years, this radio would seem out of date, superseded by new transistor designs. 1950s vacuum tube consumer products were notoriously unreliable and short-lived. In fact, my first job, apart from picking apricots, was fixing people's TV sets at the age of 14. This consisted primarily of replacing vacuum tubes that had embarrassingly short lives. But I digress. I acquired the Heathkit, assembled it, then spent years afterward making imaginary improvements to its simple circuit. Meanwhile, I acquired a ham radio license, then designed and built transmitters out of parts salvaged from broken TV sets. The AR3 had 4 vacuum tubes that actually did something, not counting a simple rectifier tube that provided the voltage the tubes needed. Because of the high cost of vacuum tubes, it was common to make a tube perform more than one function. In this radio, the audio preamplifier doubled as an oscillator that made CW and single sideband reception possible. Notice the outdated terminology in the schematic and catalog page. What we now call AGC is called automatic volume control. Frequencies are described in multiples of cycles per second. Terms like kilohertz were 4 years away from international adoption and about 20 years away from everyday speech. Memory is a peculiar thing. I can remember building this radio in 1956, but I can't remember the details of some of my NASA electronic designs from 25 years later. At age 12, I remember building a particularly powerful ham radio transmitter, thinking to myself, people will hear my voice 1,000 miles away. It never occurred to me to ask myself what I would say or whether anyone would care to listen. Thanks for visiting. Please like and subscribe. And here's my favorite way to end a video. Imaginary children beneath an imaginary sky.